Hello and welcome to Compiler, a stream about working on SpiderMonkey and implementing parts of the TC39 specification, the JavaScript specification. TC39 is the committee behind the language, behind the evolution of the language, and the standard is called ECMA 262. So what we're doing here today, if you're new to the stream, is we are implementing fixes for inconsistencies between the SpiderMonkey engine and the rest of the JavaScript engines, like whether or not we're spec compliant and we're doing things as expected on JavaScript. So that's the concept behind this stream. Please feel free to ask questions, interrupt, ask for more details, anything like this. This is open. It's for you to ask questions and to get a better understanding of how a JavaScript compiler works, how the specification works, etc. So I'm here as a resource. Also, it's likely that some of my colleagues might be in the chat, so if you ask a question, maybe someone from the SpiderMonkey team will answer your question directly if I don't get to it. Ian just said hello. He is one of the engineers on SpiderMonkey, and also we have Jan as Yandam, and I don't know if Leafless maybe, I don't know. People have different nicknames, so but Jan and Ian for sure, great resources to ask questions to, and I will try to answer as many as I can as well. I may have over-prepared for this because I wrote you folks a zine to help with the explanation of stuff. Now, if you're not getting your updates from Twitter, you might not have seen it, so I'm just going to post it into the chat right now. And this is something new, something I'm trying. The idea being that these streams are going to have a cyclical nature. We're going to be covering similar ground over time, and we may need a shorthand, especially for folks who are new to the stream, to be able to catch up. So these zines, I'm going to be writing them as I do the streams, and you can dive into those if you need some more information, and I'll be introducing new concepts or adding to the zines over time, stuff like that. Just some visual handbook about what we're talking about. Cool. I also recently wrote a blog post about this stream and my thoughts about it. I'll link it later in case you're interested in reading more about what I'm thinking about this. So, without further ado, unless there are any questions, if anybody has any questions. Ted from Moz T. Campbell is also there. And Mike is also from Mozilla. We have a lot of Mozillians there. So, if there are any questions, I'll take those right now about what we're going to do, and then I'll start the introduction for the problem we've been solving over the last 3 streams, which we're going to pick up now and dive into a bit deeper. Caveat. Because I did the zine, I didn't fully finish my prep, so there's going to be some spontaneity in this stream. Okay, let's take a look at our problem. We want to look at this one. So we started this looking at a bug. Actually, more specifically, it's a test 262 bug, but I'll show you the exact test in a second. Maybe I'll even open it. Maybe it's this one. Also, Black Lives Matter is still going on. Protests are still going on in the US. This is very important. Lots of the committee members feel very strongly about this, so we have been messaging our support for this movement. Right, so the test that we're looking at is the prefix increment test. It looks like this. We have all of these tests in trees, and just to quickly reiterate what the problem we've been solving in the last couple of streams, we're solving a problem around consistency. The problem that we looked at is basically when you evaluate just this part of the expression, it behaves differently from when you evaluate this expression as a whole. And we don't want a difference between the way those two evaluate, so we're trying to fix it now. So far we've partially fixed it. I have a patch up here, which we modified in the last stream, where we solved the problem. Essentially, we needed to check if the object was coercible into that it wasn't null or undefined. We needed to move that instruction to after we had evaluated the argument. So if we go back to the test, you'll notice that there's this argument here, and our old behavior was we would check if base was null or undefined before we evaluated this, only in the case of having the increment behavior. So that seems a little bit weird, because if you have the regular behavior, then it evaluates correctly. And that's what we were fixing. We did an initial fix, but there are two problems with that fix. The first problem is that, and I'm going to bring up the comments that were made on this bug. It bloats the bytecode. We're emitting twice as much bytecode as we were before. And the other one is we have worse error messages. So we want to make sure that our error messages stay just as good as they were. And this bloats bytecode issue, it's just something that it isn't ideal. In our last stream, we talked about whether or not bloating the bytecode had a measurable impact on the performance, and it didn't. It was just a few milliseconds or something. It was a really tiny value. It wasn't significant enough for us to change things. But the worse error messages is a problem, and we should figure out a way to fix that. So Andre Bargul, he wrote this initial test, actually. So here we have Andre, 2015. He wrote this initial test, and he's looking at the fix that we did, and he's saying, well, this is what we're currently emitting, and it's great because we're not emitting extra information that's just bloating the information. But with our fix, we have 3 new bytecodes added: a swap, a check object coercible, and a swap. And on top of it, he shows what the problem with the errors is. What we had before was can't access property of null, and now we have null has no properties. So that's the change. That's what isn't ideal. Actually, the case that he's showing here, it happens in the current engine, but we've made it. It happens in the current engine in these 2 cases, but we've made it worse. So basically, that's the issue. Yes, this is fix 1 bug, create 2 more bugs. Now, coming to the solution that we're going to look at, we're going to look at introducing a new bytecode, prepare set element, which will handle what these 4 bytecodes were doing. This would solve the bytecode bloat problem, and it would also solve the problem with error messages, because we could check on that and make sure that we give a good error message in that case, because that becomes a special case. We become aware that something special is going on here and we can react to it. So, right, now, one question you might have is, what the heck is bytecode? If you're coming from a JavaScript application background, if that's what you've been doing, maybe you're self-taught. That's where I'm coming from. I'm a self-taught developer. I don't know very much about systems programming. So this is a learning process for me, and maybe you have the same questions as I did when I was learning stuff about this system. So I'm going to share with you my perspective on these things. Let's start at where the documentation is. So we have documentation about what bytecodes are available for SpiderMonkey. And we have things like undefined, null, these are the constants that you'll find in JS, along with a number of other types. And then we have things around expressions, and binary operators like equal and not equal, you probably recognize those, and a number of other things. What this documentation is telling us is a bit of information about this. Let's call it a language. It's a set of instructions. I'm going to dig into it a bit more. And it's giving us a stack, and it's telling us, well, if there is a stack, maybe it's just taking 1 value, maybe it's taking 2. In the case of add, it takes 2. L value and R value stand for left and right value, and we'll take a look at that in a second. And it gives us a description about what it does and some more information that isn't necessarily going to come into play right now, but maybe we'll take a look at it later. So I'm going to switch over to my drawings and hopefully clarify any questions that you'll have about bytecode before we start writing our own bytecode. So, what is bytecode? Now, this question might come back to what is a programming language, actually, or rather than what is a programming language, because bytecode, you could say it's an instruction set. You can do everything with it that you can do with a conventional programming language. But what's the responsibility of a high-level language like JavaScript? And as a proposal, I would say that the purpose of a high-level language, such as JavaScript, is to express the intent of a given program. Here we have a little character say, do this thing. Express that intent in a way that both works for communicating to other programmers what your intent is, communicating your intent back to yourself so that you can maintain your code base, and also being machine runnable. So a programming language has this interesting trio of consumers, which is the programmer who wrote it, other programmers, and computers that it needs to communicate between. But, just going directly off of that, the text file that you write when you're programming, it's a little difficult for a computer to efficiently look through all that information because there's a lot of extra information that isn't really necessary for the computer. Let me get a pen out. Oh no, I lost my pens. Like, for example, you don't really need to know, like the computer doesn't really have a concept of do. And it doesn't really know what this is. It doesn't really know what thing is. It's really good with numbers, right? Like 1, 0, 0, 0, 1, whatever. It knows numbers really, really well. And to work with language and to understand intent from language, not its favorite thing. Let's put it that way. It's possible. You can always do everything, but it's not ideal. So what we do is we have a well understood system of doing things, which is basically conventional compiler interpreter structures. So you start with a source file and you tokenize it, you parse it, and then you emit it. And what this is, what do you emit when you emit it? You're emitting bytecode, a special format that is that doesn't worry about human language. It's much more efficient. It's really about representing all of the things about the program in a much smaller format as numbers, as constants, etc. And passes that over to the interpreter. So the interpreter can run that much faster than trying to figure out what all of this English means. And this is sort of the point where the front end of the compiler and what we call the virtual machine, where the interface is between those two. Does anybody have any questions about this so far? Sorry for the messy drawing. All right, I'm going to keep going, but feel free to ask any questions, and if I miss them, then I will catch them later, or someone else will catch them in the chat as well. So, moving on, the next thing that we have, the next thing we're going to look at is how does this representation work? One second, that was a little bit off screen. So, let's say you have a source code, add.js, and I have a special little bit of code here, which is from the previous episodes. You might remember we talked about the disassembler, the Disassembly Helper function. And that we're going to use that to understand how bytecode works. So here we have a pretty simple function. It's a lambda function. We're taking two variables a and b, and we're just adding them together. Nothing really complex about this code. So we say a plus b. When we do this, and it goes into the front end, so we're completely in the land of the front end of the compiler, it then gets transformed by the parser into something called an abstract syntax tree. It's an AST. And And it might look something like this. If you're familiar with JSON, think of a JSON object, and a JSON object that has like things that stretch out from it. So you would have a property node, you would have a property left, and it would have some stuff inside, and the node has like add, the node has a type, it's add, it has two properties on it, left, which probably also has a type on it, like int. It's always harder to write when you're talking. And then inside of it, it might have a value or something like this. So we output this format called an AST. And just to give a little bit more information about that, you would have something like a node that has two children, like so. And this would be the add node, just to think about it graphically, because that can help. And this would be 1 and 1, but this could become more complex. So let me just get rid of that. So for example, if this was, if we had a third variable here plus c, we could say that we have add, and on the left-hand side, we have a. So we're looking at this operator here, and this is the left-hand side of that operator. Then on the right-hand side, where we had b before, what we'll have now is another add based off of this, and then this will be b and c. All right, there might be some questions. Let's see. Okay, so we have a sidebar. Is there less emphasis on writing human readable code for compilers lower level languages? That's a great question. We're going to dig into that in a second, and you'll see how the bytecode is made to be human readable, even though it's much more, the emphasis is it being machine readable. It's really important that we can understand what's going on in the system, and for that we do need English language, because if we're working with just numbers, it's going to get really, really hard. So the AST already knows what A and B are. It knows that it should get them. So for example, in this, it knows that it's expecting to get an A and a B. It doesn't know the absolute value of what that A and the B are in that specific node. Like, for example, here we don't have A and B defined. It'll be defined later. So it'll know where to look, and maybe that answers the question. It knows where to look. And then... okay, so there's a couple of questions around compilation. Could you expand a bit what you mean? This was Matthew is covering one question. I'm going to let him do that. Does this mean that JS is actually a compiled language rather than an interpreted language? Right. So that's a great question. What does it mean for something to be compiled versus interpreted? Because the bytecode is something that we use for the interpreter to run JavaScript. But you could argue that we're compiling to bytecode. In fact, at that stage, it's still an interpreted language, because as far as I understand, and someone please correct me if I'm right, if I'm wrong, we're not compiling down to machine code, we're compiling down so that it's efficient for the interpreter to understand what's happening with the code. Is this functional programming? I'm not too sure what that question is. JavaScript is both compiled and interpreted, that's right. Yes, the lines are blurry between interpreters and compilers. All right, it looks like folks are having a good back and forth. I'm going to let you folks look at the difference between interpreted and compiled programs in relation to JavaScript, and I'll continue with the little tutorial I have here. Okay, cool. So basically we get an AST like this, and that can be also represented in this form, which is, if you know JSON, it looks something like that. It's an object with nested fields, and it can nest very, very deeply. Okay. So, the next question we might have is what is going on with this compiled code. And how can we see it? Now, you might recall from a previous stream that I showed you the output of the disassembly code. Ooh, I just realized that I made a mistake and we might have to suffer because of it. Let me see if I can actually run the run things. Can I run things? Please tell me I can run things. Oh yay, I can run things. Good. Okay, so let's take a look at some. Let's take a look at that output. And ooh, oh no. Is that big enough for people? I don't know. I don't know if that's big enough for people or if I should make that larger. But let's clean that up. Okay. Okay, so disassembly. Let's take a look at a piece of JavaScript in the SpiderMonkey shell, and we can see how the bytecode looks in that case for this addition addition function. So actually, let's make an add.js. Oh, I'm already in the shell. Okay, and what we can do is add. Do I need to do this? I might as well do this. We can just write dis, just like in the webcomic. You can write dis, and then we'll put in a lambda function in here, a, b, and then arrow, and say arrow, and say a plus b. And that should work for our purposes. So that's exactly the same thing that you see in the zine. Okay, now we can run it. And I don't have an alias for my shell. I'm in a specific, I'm in my build directory for SpiderMonkey, and I'm accessing it like this. Other people have aliases for it, but I'm lazy and never did it, and I've been fine using it like this. Some people mentioned that they would like to have some help building SpiderMonkey. I will do that once we finish this initial cycle, so we'll do a dedicated stream to building, running SpiderMonkey on multiple environments. But coming back to the topic at hand, let's run that. And what we get here is a dump of information. We're going to ignore everything below this line. We'll look at that a bit later. Does that work? Oh yeah, I need to also alias Mach. Anyway, okay, so what we have is this dump of information. What is it telling us? What are the pieces of this thing that we're looking at? We have here a little bit of annotation that tells us something that we can use. First is this location header, and then the second header is the operator. We have the beginning of a main program, and then we have a lot of numbers here. Then we have some information about the operators. So we have get arg and then 0, get arg 1, and we have information over here. What this information is, I don't know if you can see my mouse, I don't think you can. What this information is telling us is, like for example this. It's telling us what's on the stack, on the value stack. And this is telling us the instruction set that's being followed by this program. Ooh, there's lots of questions. Are there any benefits for regular JavaScript developers to know about the internals of different JS engines? Ideally, no. Ideally, you shouldn't know the internals of JavaScript engines. This should mostly be about helping you learn how an engine works so you can apply it to other places. You may get some interesting insights into how JavaScript works and how you might make your JavaScript run faster, or why certain things happen in JavaScript, or maybe why certain things were specified in specific ways. So you would have a lot of contextual knowledge around JavaScript. And that might help you with your work, but I don't think it's essential. It's something that's there for your interest, and it might also be interesting to see how this applies to your work. I would love to hear how people apply this in their work. So, yes, and Ian has a great comment on that. Okay, cool. So here we have a set of instructions. Like, it's basically like the JavaScript that we wrote. We have this add and then return readval. But what do these actually mean? So let's dig into the documentation around it. And what we have here is we have the add here, and then there's also getarg. So if we read getarg, what it tells us is it has an operand, and it has a U16 argument number. So the stack is, I'm actually not too sure how to read this, I just realized. I will figure it out later. And it pushes the value of an argument that is stored in the stack frame or on an arguments object. So actually I should have drawn this out as well, but this has to do with how information is stored when you're building up when you're building the frames. I'm not too sure how to put that. This isn't an area I feel super comfortable with, so I'm going to have to also do a little bit of reading there too. I did know this at one point, and now I feel a little bit like, oh gee, I'm not so sure if I know it so well. But anyway, there is a stack, and it's stored on a stack frame, which is created for, I think it's every closure. I'm not 100% sure. People correct me in the comments if I'm wrong. We'll figure it out later. Moving along. So anyway, this is interesting. It tells us that we have something, an argument number, and we can see that in the programming. Right here we have the 0. But what does this mean really, like if we really dig down into the thing that we're working on here? And I should have more drawings for this. All right, cool. So what we just looked at was, we looked at, we just covered a few interesting bits of this. We looked at what these are, and we looked at what these are. One thing we didn't mention is what's going on here, and that might be interesting to some of you. Like, what do all of these zeros mean? What does this 3 mean, this 6, this 7? And actually, if you take this, the difference of this offset is the size of the bytecode. And we'll see that right now in action in a second. So here, the difference here from add to return, add has a size of 1, and the get args have a size of 3 each. And then return is 1, and readval is 1. All right. Let's zoom in on just one of those. We're going to look specifically at getarg0 and how that works deep down, like in terms of how it's implemented fully. Okay. What we have is, and I think this is probably in the way. What we have is, if we inspect the code, what we'll end up with is a number of addresses. It's from the program counter. So as a program is running, we keep track of where we are in the program in memory. So we store a number of instructions. And I'm drawing these as rectangles, but these have like actual addresses in memory. And as we move through the memory, the program counter, the PC, moves each time. And it iterates over what's in, it increments as we move along the program. Let's see what that actually looks like in the engine. And there's a nice spot where we can put a breakpoint to discover this, and I'm going to do that now. Too many things everywhere. All right, cool. So we can go in here and take a look at how that works. And so I'm going to use LDB. Oh, I've got some questions. I just realized that this is in the wrong spot. There we go. Are all the bytecode instructions the same length in memory? That's a great question. They aren't, and we're about to see that in just a second. I'm going to add a breakpoint in a really specific function. I'm going to have to go all the way back because I was trying this out. I'm learning this myself right now. So, where is my breakpoint? I should have set up my reverse search. I'm gonna, ooh, oh no. Will I be able to do this right now? Because I tried to build and it didn't work. If it doesn't work here, I'm going to try and rebuild, and then we can see what we can do. Okay, so it's going to be building. It's going to be slower because I'm streaming right now. And then we'll see if we can get the information that we need. Because I need to build it right now, we might run out of time a little bit, but it'll be fine. We have lots of stuff to cover, and people are having great conversations, so that's perfect. But while we're waiting, what we can do is we can take a look at it in Searchbox, which is the greatest thing. So in Searchbox, you can very quickly search for anything that you need in the entire browser. So Firefox is a monorepo, and SpiderMonkey is part of that huge repository. Specifically, we can take a look. I think if I just erase this, we should be able to see it. Oh no. Searchbox, what are you doing? For example, JSSRC. So in this directory, we can get all of the files related to the SpiderMonkey engine. And inside of it, we have this function called decompilepc. This is used by the disassembly function. This is used by the disassembly function, and we're going to stick a breakpoint right in there so that we can see what's happening when the disassembler is trying to give us the information. The Disassembly Helper function is a really great place to like sort of stick your head in and be like, what's going on and how can I find more information? Because in there, there's lots of stuff available to you to play around with. So that's what I'm going to do right now. And it built super fast, so let's do that now. Okay. All right, so let's add that breakpoint. I'm adding it to line 1733, but you could add it earlier. It depends on where you want to see stuff. It's just after we define the opcode as well. And let's run it. Cool. Okay, cool. We stopped at line 1733, and what we can do is we can start exploring the world that is this thing. So for example, we can print can be shortened to P. We can print what's in there. For example, we can print what the opcode is, which is what's being defined here. And the very first thing that we're getting is the get arg opcode, but we can dig down a little bit deeper and try to understand more of what's going on in there. So for example, we can also print the PC. And when we do that, we get an address back, which is pretty neat. And when we look at that, we can explore what's there. So for example, do I have anything good? I was playing around a lot. Okay. I can use this LLDB method, x/1x. I have a lot to learn about how to do inspection of memory in LLDB, but bear with me. I found this super interesting. And what we end up getting back is, well, actually, we're better off just printing the PC. What we end up getting back is something that is a number. That is a little hard for us to understand what that is. But we can also, PC is the program counter. What can we do to break this? What can we do to explore what we're doing here? What can we do to understand this PC a little bit better? Well, what we can do is add 1 to it, because that should be 1 ahead of where the program counter is. So let's see what's there. Oh. Wait, that didn't work. Let me instead do this. Okay, cool. That works. So now I've printed the value, the thing that's at program counter +1, and it says there's no value available. And then I can keep incrementing it. I can do it +2. Again, there's no value available. And then +3, suddenly there's a value available there again. I find that pretty interesting. I might be the only one. But then the question is, what does that value actually mean, and why do we have 2 empty values after the first one? Also, let's recall if we look at the drawing, that we have, that's the wrong drawing. I wanted to show, not this one, but this one. Recall that we have a length of 3 here. Let's see if I can draw something for you folks. Right here. So, if we come back to this, and let's undo some of the craziness that I just did. Okay, back to where we were. So recall that getArg has a length of 3 and not a length of 1, which isn't true for all of the bytecode. So let's explore a little bit more inside of the bytecode, just like looking at what's ahead in the program counter. And Ted just mentioned in the chat that if you do JSOP with a pointer to the PC, you'll actually get the bytecode, and let's do that, just to show you that that's the case. I wonder if I can do it exactly like he wrote it. Let's see. No. I had another way of doing it. I think it was star JSOP star PC, was that it? No, where was it? I have it in here. It's just deep in the back. Somewhere. There we go. Okay, so this is also interesting. So if we do it on PC, on the current program counter, we get back the getArg by casting it to JSOP. That's what we're doing here. I think that's what we're doing. I think that's how you say it, casting. And then one thing that you might have noticed that was interesting is if we advance it 1, it'll be undefined. It says that it's undefined, but we didn't push anything onto the stack that was undefined. So something funny is going on there. Anyway, let's come back to what we were doing before, which is kind of inspecting, like, step by step what's on the program counter. So that's if we look at the first one, and then if we go +1, we have, something's wrong. I wonder what I did that's wrong. Oh, I think I know. Yeah. X, spaces, too many spaces, and then 2, there we go, and then 3, and then 4. I'm actually getting the wrong thing right now. It's not what I expect, but that's okay. What's important here is what we're looking at on number 4 is the same as what we, well, not the same actually. I wonder why I'm not getting the same output as I was getting before. Maybe it's because I am pointing to the wrong thing right now. So if I grab that, and then x1x, there we go. I think, not quite. Something's going wrong, and dang, something's going wrong. I'm not too sure what I did wrong. What I wanted to show you is how the value for the index appears, but I have it drawn out. So we can just look at the drawing and I'll figure out what's wrong with my setup next time. So let's go back to the sketch. And actually I have it all I have it all drawn out for you here. Namely, that the value that we're looking at, when we look at this one, this is one number, BA, and then here we have another one, and we know that getArg is of size 3. So what are these two things doing? This is telling us in U16, which is a larger size, it's double the size of a byte. So a byte is 8 bits, so 8 zeros or ones, which can express a certain size number, and U16 is double that. It has twice as much room in it. And that this here is expressing the value 0 in U16. And the same we can say about this value here. This is expressing the U16 value of 1. Yes, little Indian is involved. I did not do a CS education, so I'm not 100% comfortable with little endian, but it is involved. It's actually in the in part of the stuff I wanted to show you. So we have this get arg number. Actually, one question we might ask is, how does the disassembly script know what... Oh, maybe... Oh, Yandem just said something that was really useful. PC +1. Ah, interesting. Didn't know that. Does it do what I expect? Not quite. In the decompile function, we have some stuff. You can just poke around in this function and see how the different bytecodes are handled. And for example, get arg uses this get arg no. I guess it's number. Not sure entirely what it stands for. And then we can click on it and go to the definition, which says get uint16. Then we can click on that. And then in here, we actually get an offset by 1 from the PC. Huh. People are saying interesting things in the chat, so I'm going to try them. Let's try. Is it the B that I'm missing? Might be. Yes. Oh my goodness. Thank you, folks. I was missing the B, which just shows that I'm totally new to this. So right, here we are at the very first argument. So get arg 0, and let's see how it looks. So if I add 1 here, we're going to have 0x00, and then if I add 2, we're going to see the same number. Then if I add 3, we now see the same bytecode appear. And then I can add 4, and then it's slightly different because we're getting the number 1 expressed in like 2 bytecodes that together unify into U16. And then we finish it. And to answer a question that was asked earlier, are they all the same length? Well, they aren't, because now I'm at PC6, and I can keep going up, and then PC7 is actually something, we're getting into different bytecodes. So PC6, actually, let's go back in history. Here we are. This is the add function. And then if we keep going up, we get to return. And add has a length of 1 rather than a length of 3. So, are there any questions, any further questions about what bytecodes are? Like, a bytecode is really the names we have for bytecodes aren't the thing that the machine knows. So for example, what we read here, this add bytecode, is actually expressed differently. It's expressed as this number to the machine. And then the machine knows in certain cases that it needs to do different things depending on which bytecode it saw. For example, if we go back to our disassembly thing, it knew that, oops, that's the wrong thing. Let's go back a couple of steps. It knew that when the JS opcode is get arg, it needs to do specific steps, which is get the argument number, which means that we are looking at 2 more bytes, combining them as a U16 and getting the argument number from that. Whew. Okay, cool. So let's get back to work and implement the fix, which I don't know if 15 minutes will be enough time, but we'll do it partially, and hopefully we can go from there next time. Okay, let's get rid of all this. This was fun, but okay. So where I am now is on top of the work that we did in our previous episodes. So I'm using an extension called whip for Mercurial, which is HG that you just saw. And this is the whip for stream that we did last time. And it's built on top of the previous patch that I pushed out and that we looked at on Fabricator. So, working on top of this, what we want to do now is we want to add an opcode. I don't need this, I need And this is where Searchbox becomes super useful. What the heck is opcode? I am searching for opcode on Searchbox so that I don't have to look at it in my file. Opcodes.h is on VM. There we go. Okay, neat. So this is the file where all of the bytecodes for SpiderMonkey are defined. And the bytecodes that we're trying to replace, as a reminder, are and its element op emitter. Let's go into there. All right, so a quick refresh. What we did in the last streams was we added this. Specifically, we added compound assignment so that we could cover more test cases. And we have a swap, a check object coercible, and a swap. What we want to do, and on top of that, we've got this toProperty key. And our ideal dream of this code is to basically delete all of what we did last time, go over here and rename this to prepare set lm. So we want to introduce a new bytecode and not have to do any of that extra work that we were doing. So I'm just going to bring all that stuff back so that we can use it as reference. And let's take a look at how check object coercible is defined in opcodes.h. So here we are. It starts with a comment, and then there's a macro. I'm just going to look at what the macro is doing without looking into the macro. We're just going to modify values on this thing. So here we have some information about it. It's in the category objects, iteration, operands, and then there's a stack here. It takes one value and returns that same value. And it gives us a little bit of information about the spec. So I'm just going to copy this for reference. We're not going to actually use it later on. Let's take a look at toProperty key, which I'm going to base my work off of. I'm going to just dump this information, cut a whole bunch of stuff out, and I'm just going to grab this and compare the two of them. I don't think we need this for now because it's not here. I'm just going to pretend it's not there. Just for now. And we'll talk about it a little later. And what I want to do is basically write my own thing for this. So prepare set lm. And then everything else looks like it's pretty much the same. And I'm going to do a little bit of changes here, and I'm just going to add a little bit of information about what I'm doing so that I don't forget. And what I'm doing is let's go to the spec so that I can remember what I'm doing. Let's talk language specification. So fire object coercible. Let's actually search for it. Fire no, that doesn't help. Require object coercible happens evaluate property access with identifier key and expression key, and I think we're in the right spot now. Property accessors. We are looking at member expression, this line here, and then in a previous stream we actually went through and read this in detail. Essentially, when we have this case, we go in and do these steps, and eventually we get to this point. And I'm going to jump over there now. And in evaluate property access with expression key, we have first require object coercible, then toProperty key. So in my code, I'm going to write something to that effect, approximately. And I'm just going to add stuff in here for now. I'm going to remove that and actually replace it with this one. And say that we have the... I'm not too sure what to call it yet. Oh, I took off the... Oh no, I did everything right. we have an object. So we now have a stack of 2 that we're dealing with. And throw a type error if it's null or undefined, and then do the same thing as toProperty key. Just checking in on if there's any questions. I'm not sure where you're looking for the bugs, but yes, we do have a lot of bugs. Okay, cool. So I've created a prepare set element, and I also know that we have a thing in here, which is for each trailing unused opcode. So I've actually added an opcode before, and I made this modification in the past. I don't actually know why we need to do it, other than that we're by adding a new opcode, there are fewer unused opcodes, so I'm deleting this. And my colleagues in the chat might have more details about what exactly this is doing, and if there should be something else added here. I don't think so, because we go up to 255, so it seems like we're filling up an entire space. But I'm not 100% sure, because this isn't where I normally work, so this is an adventure. Okay, cool. So we have the opcodes done. And now I'm going to jump over into the interpreter, which is where we're going to implement our behavior now. Because if you can recall, before our behavior was implemented by bytecode, now we're going to take that away, use a custom bytecode that now needs to be taught to all of the other levels of the compiler. So the interpreter, the JITs, well, the interpreter and the JITs, that's it. So I believe it's in VM/interpreter. Yes. Oh, good memory. All right, cool. So I'm gonna again base my work off of the work that others have done, because the system exists already and it's something I'm learning myself. And I'm just gonna look at property key again. And looking at this, I don't think that this is the toProperty key that I want. This is the one that I want. So we have a case statement in here. We're somewhere deep in a case statement covering all of the bytecodes. And it's doing some steps. So let's try to understand what those steps are. We have something that is looking at the registers. So before, you remember, we were working with a stack machine. Now we're looking at registers, and the register that we're looking at is the stack pointer. So we take the stack pointer and then we -1 from it. So I think the way that I'm looking at this, the way that I'm thinking about it, is that the stack pointer is essentially the program counter, like something analogous to that. And we're -1 from that. So we're taking the thing previously off the stack and using that. And then we have a result, stack handle at -1. This I don't fully understand. This is something I have to learn myself. And then we have a function toProperty key operation. The context, the value that we've defined here, and the result that we're going to output the result to. And if it doesn't work, then we go to an error, and then we finish the case. So that's what the interpreter is doing with toProperty key. All right, so I basically want to do what toProperty key is doing with a slight modification. So prepare set lm, just gonna steal it. We want to add check object coercible to it. We have that here, and I'm just going to steal all of it so that we can look at it side by side. All right. And let's comment that out just so that we have it there. Okay, cool. And I'm going to just copy it and smack it right in the middle here. Okay, so what is this happy code doing for us? Where did that get moved? Something happened. Ah, yes, something did happen. I did bad copy paste. Okay, so step by step figuring out what this is doing. So once again, we are creating a variable called checkVal, and we're assigning it to the register -1 again, which actually isn't what we want to do. Let's take a look at the bug again, because there's great information in here. If we look at the stack that we currently have, what we want to look at is get arg0. We want to look at this O. We want to check the object if it's null or undefined. And if we get -1, what we'll get is this P. So we need to look at this one here instead. And before, the way we would do it is by swapping the positions in the bytecode stack. In the stack. Using bytecode, we would swap the things on the stack. But now we don't need to do that because we can just do that in the interpreter itself. Back here. So instead of -1, we want to go -2 because it's present 2 steps behind, as you saw. And then what we want to do is basically run the checks that were on check object coercible. Just checking again what the steps we wanted to do are, which is here. And what we want to do first is we want to require object coercible, and then we want to transform it into a property key. So, taking a look at the steps that we have here, we are checking if the object is coercible, and then we are transforming it into a property key. That should be enough, which means that I should be able to just go kill that and say, okay, cool. Does anybody have any questions so far about what I did? While people are thinking if they've got questions, I'm going to try and build this thing. I tried to build it before, and it totally failed. Why is the volume so low? Is my speaking volume very low? Because I can try to bring it up a bit. Okay. Okay. Do people have any questions? We're coming to the end of the stream, so one thing I'll note right now is that this isn't going to build because we haven't finished everything that we need to do. This is just the first part of what we need to do. But since we won't be able to test this, then let's just go to questions right away. Are you going to implement this bytecode in the JIT separately for each architecture? Yes. Oh, I'm quite compared to other streamers. I'm not, yeah, maybe I should check how other streamers sound. Next time that I do this, I'll make sure that I do an audio check with other streamers, because I just did an audio check with my headphones before I went ahead with the stream, so thank you for the feedback. I'll definitely do that. Any other questions that I can cover? Jackie asks, this all started from fixing one broken test in test 262. Are SpiderMonkey bug fixes usually this involved, complicated? So I actually picked this test 262 bug because it looked simple and like I could do it rather quickly as a test. I had planned it initially for 3 episodes, and we're going into probably 5 episodes. This is the 4th one. So I had thought this was going to be simple. It turns out it's far more complicated than I thought. Part of that is that this is a long-standing bug. It's more than 4 years old. And this is wrapped up in other issues, other inconsistencies that we have that we'll need to fix. Depends on the detail of the operation, but something like this probably uses the abstraction and macro assembler instead of being implemented for each architecture. Yeah, so in terms of implementing it for every single JIT compiler, we need to implement it for the interpreter, and we will need to do some special work to get it running on the JITs, and we'll take a look at that in the next episode. Do I know if dividing is slower than multiplying by float? I have no idea, actually. I'm not sure. Someone else might know the answer to that. All right, so we are at time, and what I'm going to do, since this is still compiling, but I know that this is going to fail actually because we haven't done the work on the baseline compiler, and I already tried to run this and it did fail because we need to do a little bit more work. But we'll pick this up from this point in the next stream, next Friday. I will try to make sure that we have some more zines for you to look at if you like them. So please give me feedback if those worked well and if they helped you with learning.